Good afternoon, everyone. Thank you for joining. My name is Gaurav Agarwal. I work at Marvell in Custom Solutions Group. I'll be talking about CXL Near Memory Compute acceleration. How can they help break memory wall for AI and other important workloads and provide flexibility and scalability for optimal performance, energy efficient and cost-effective solutions? There is plenty to cover in a short time, so let's jump right in. First, to set a context, a quick refresher on some of the key challenges related to the memory. The compute horsepower, as in terms of flops, has been growing at a much rapid pace as compared to that of the memory bandwidth. The gap between compute and memory has been widening, as seen in this chart that you would have seen earlier. With models rapidly growing exponentially in size, and so is the sequence length, many of the important AI workloads, particularly in serving, have high memory bandwidth requirement. As a result, the memory has become the bottleneck, either in terms of capacity or bandwidth or both. The problem gets worse as many of these workloads exhibit sparse, irregular memory access patterns, due to which the effective bandwidth ends up being a fraction of the peak. The memory wall not only affects the system performance, but leads to the poor utilization of precious AI accelerators. The workloads vary in terms of arithmetic intensity, memory footprint, latency, throughput, and other factors, due to which the requirements on the underlying infrastructure vary, which means flexibility is needed as far as the underlying infrastructure is concerned. But the integrated HBM on the AI accelerators create a fixed compute to memory ratio, which doesn't provide the needed flexibility. There is a need for flexible and scalable system design for energy efficiency and cost-effective solutions. Here's a step in that direction. Marvell's Structura CXL accelerators with near memory compute capability. In this example, the baseline is a single proc system with 64 cores that comes with about 400 gigabyte per second of memory bandwidth. That equates to a per core bandwidth of about 6 gigabyte per second. Let's scale it up with Structura controllers. Each controller provides up to 200 gigabytes of DDR5 bandwidth, with low latency to the 16 server-class ARM Demeter cores for near memory compute, and terabytes of DRAM capacity per controller. And the flexible scaling is energy efficient too. As can be seen, with only 2 of these accelerators, we have doubled the overall memory bandwidth, increased the compute cores by 50%, and each of those cores provide double the memory bandwidth of the main CPU cores in energy efficient way. Now let's take a look at some of the real world workloads that are affected by the memory wall. On the AI front, personalized recommendation systems serving, large language models inferencing, retrieval augmented generation, these are all memory bound. Due to their large memory footprint, they require large memory capacity. They exhibit the sparse and irregular memory access patterns and operate under strict low latency requirements. Fortunately, these workloads are shardable, that is, can be partitioned, which makes them suitable for the heterogeneous compute environment, such that the operations with low arithmetic intensity, large memory bandwidth requirement, and capacity requirements can be performed on the near memory compute device, whereas the compute-intensive operations on the AI accelerators. Let's take a closer look at a couple of these workloads. DLRM. This major workloads for hyperscalers like Meta and Google has been a hot topic, with significant activity on optimizations using different approaches. Let's revisit this important use case, this time with NMC accelerators. Embedding tables make up the key component in the DLRM system and generally have a very large memory footprint. The access patterns are typically small, gather, scatter, and irregular. It's important to note that the system performance is highly dependent over embedding table lookups and related operations like SLS operator of the Caffe2 framework. Now, considering that embedding tables being the key component, what would be the optimal placement? Obviously, distribute them across the XPUs could take tens or even hundreds of those XPUs. But those precious tensor cores would likely remain underutilized because primary reason to add XPUs would be for the memory requirement. Clearly not a cost-effective or energy-efficient option. The main CPU of the host is another choice. But using up those host CPUs with large number of cores just for memory expansion isn't the best option either. Typical systems have multiple XPUs per processor, like 4 per socket. So once the memory bandwidth of the socket gets divvied up across the XPUs, each XPU won't have the adequate bandwidth anyway. Okay, so how about we put it on the NMC like Marvell's Structura? That brings in 200 gigabytes of DDR5 memory bandwidth. And with the strong SIMD vector engines, not many cores are needed to handle the embedding table lookup and related operations. And of course, the dense operations that are best performed on the XPU can remain there. Best part, there is flexibility of controlling the ratio of the XPUs and NMC. We have created a functional POC in our lab with a system that looks like this. On a CXL-capable x86 host with NVIDIA GPU, we added prototype reference boards in place of a Structura because the silicon's not available yet. But the reference board had similar hardware, exactly the same compute cores. On the software front, we used Meta's open source Glow framework. The DLRM workload partitioned nicely into 2 parts with very distinct characteristics. Compute dominated continuous features involving MLP processing, suitable for the XPUs, and categorical features that involve embedding tables with huge memory footprint, but with low arithmetic intensity, like the SLS operation, perfectly suitable for the near memory compute accelerators for the NMC. And the initial results are promising. As seen here, comparison between 2 scenarios. One, when the embedding tables placed on the host CPU attached memory, meaning host system memory, and the other in which embedding tables are placed on the NMC device. The results are similar in that only about 8 cores for these workloads were needed to saturate the memory bandwidth. We vectorized the SLS code, and the optimization yielded 5x performance improvement. This is a good example of low arithmetic intensity workload that really benefits with increased memory bandwidth per core. Okay, let's take a look at LLM inferencing workload as well. One of the key concerns here is the cost of serving. Apparently, the cost can be as high as 10x of the traditional keyword search. Among the key contributors to the high cost being underutilized AI accelerator, in terms of MFU, model flops utilization. The primary reason for the poor utilization of the compute, well, the workload being memory bound. To make things worse, the models continue to grow in size as well as the long sequences that require large memory. And as a result, require more and more number of accelerators to accommodate the memory needs. This is an important workload that calls out for energy and efficiency improvements, as surfaced by hyperscalers like Microsoft as part of their published research in the splitwise paper. So this workload has 2 very distinct phases and 2 very distinct memory consumers. The so-called prefill phase, in which all the input tokens provided by the user prompt are processed concurrently, makes it compute intensive as it involves parallel processing. This phase also generates the key and value vectors for each input token that are cached in a request-specific KV cache. The model parameters is one of the two main memory consumers, and the KV cache is the second main consumer of the memory. The second phase, called the decode phase, is serial in nature, as it generates one token at a time. And since its output tokens are generated sequentially, this part doesn't utilize the parallel processing capability of the AI accelerators either. The net effect being the underutilized AI accelerators, which drives the cost. In the decode phase, the attention operator that operates on the request-specific KV cache seems like a good candidate to be offloaded to the NMC accelerator. That would alleviate the memory pressure on the AI accelerator, improve its utilization, and reduce the overall cost. This is in our focus, and we'll continue to explore this further. Okay, so the modular system design provided by CXL controllers with flexible compute to memory ratio can be really helpful in building the systems based on the workload requirements. And NMC capability provided by the server class extends endless flexible design options. Now, software is a crucial component in the heterogeneous compute equation. For our POC, we used Meta's feature-rich open source Flow framework, in addition to the ML compiler and broad support leading ML frameworks. Inherently supports optimization at different levels and also has the runtime that can partition and orchestrate the workload across different accelerators in the heterogeneous compute environment. All of these features are super critical for a heterogeneous compute environment. But we ran into many issues and limitations. We did address some of the issues and upstream those. Won't get into details due to time constraints, but a lot more work is involved for sure. Now, NMC concept in principle is really promising for broad adoption, feature-rich software frameworks and toolchain that eliminates tedious manual work is an absolute must. So, a lot of support is needed, a lot of work is needed to automate because manual options not gonna work. Partitioning of workload in a heterogeneous environment can be complex. The right split of data and compute across different compute elements can make a world of difference. For the broad adoption of custom accelerators, it is important that feature-rich software eliminates the burden on the application developers. There must be support for different type of accelerators for the backend. Many of these issues are actually being worked upon at CMS in the white paper, which is linked to this presentation. A lot of work has actually been done, and as Pankaj and others presented in the previous presentation, there's a lot more work that actually needs to be done. So, from proof of concept to broad adoption for hyperscale deployments, some serious effort is needed, which is best done in the community to build the ecosystem and standardized frameworks, tool chains, APIs, and much more is needed. And OCP community has been doing a phenomenal job. So our ask is for you to join the vibrant community and help accelerate the innovation. Help identify the workloads, way to automate, partitioning of the workloads for the heterogeneous environment with support of variety of custom accelerators. And that's what lead us to sustainable, energy efficient, and cost-effective solutions without compromising performance. Well, that concludes my talk. Any questions?
Hi, thank you. It was a good talk. We're just questioning, in one of your slides, you said you had a LZ4 compression on the CXL memory. Can you describe a little bit what is the compression used for?
So the compression, the inline compression can actually, one can mark regions of memory on the CXL attached memory region can be marked as compressible, in which case the hardware performs compression seamlessly and transparently. So it's meant for better efficiency, higher capacity, especially for those use cases where latency is not in critical path, because compression does add some latency, although in our solution, it still stays in hundreds of nanoseconds, doesn't cross microsecond granularity.
Thank you for your presentation. My question is that I think that you have two scenarios that using the single device or multi-device. So you know that the concept of the processing near memory is that processing near to memory. So if we're using two devices, there's some latency in the PCI and other things. So my question is that how many performance can be improved in terms of the multi-device case?
Good question. So this is basically no different than multi-device case for any distributed processing. Okay, parallel compute is actually an absolute must. So the way you partition and you dispatch the workload, there may be no additional overhead introduced by the multiple devices.
Then is it right that we can get a performance improvement in the data parallelism and model parallelism? Is it right?
Correct. That is one way. There are many different ways you can shard a model and distribute its processing, which is why I stated that the performance actually, right partitioning and placement of data and compute on the right accelerator is very crucial. In the previous talk, Pankaj mentioned that how you partition can actually have such a big impact that how much data gets moved as much as 73 times. So yeah, partitioning has to be done right, okay? And how you achieve parallelism, it really depends upon the workload. There is no one approach that works for all the type of workloads.
Okay, thank you.
Let me ask a quick question to Gaurav. So Gaurav, on the near memory compute side, I mean, the use case that you are demonstrating is something that is a memory that is attached to host. And then the work is distributed between what is happening on that near memory compute and then the accelerator. What would happen if that memory was attached to the accelerator itself? Does that change the model in any way?
Oh, the memory is actually attached to the accelerator itself. So
oh, I see.
the terabytes of memory, so the structural controllers support DDR5 with memory bandwidth up to 200 gigabyte per second to the onboard ARM Demeter cores, 16 of them. And the memory capacity can be in terabytes, okay? The same memory is actually in the same memory domain of the host, accessible via load and store to the host via the CXL.mem, and as well as to the onboard ARM cores.
Got it. Okay, maybe then I should.
So it's the local processing being performed for optimization, yes.
So you had, I think you had a picture, we talked about sparse computation and then the dense computation part happening on a maybe XPU, right? Accelerators. And well, XPUs basically. And then you have part of the operations which are very memory intensive or sparse operations happening on the NMC. And that means, and this is where you are dividing the work. What happens on the NMC versus what is happening on the XPU.
Correct.
And that requires the software level changes for anybody who wants to adopt the model.
That's absolutely right.
Just making sure I got it. Okay.
Yes, no, absolutely. And so low arithmetic intensity, so arithmetic intensity as in the compute operations to perform per memory load operation.
Right.
Okay, so the lower the arithmetic intensity is, better suited that workload is for near memory compute. Whereas the XPU shines when the arithmetic intensity is high.
Makes sense. Makes sense. All right. Thanks, Gaurav.